Hi, everyone. My name is William Kerber. I'm the CEO of Human Mode Robotics. My wife, she and I started this company in 2017 because we're both futurists and we just love technology. And we were excited about the challenge of building intelligent multi-use robots. So that's been the focus of our robotics program. We're located in Oklahoma City. We recently built a new shop here to support better fabrication equipment. But like for many of you out there, there's not a lot of robotics companies around here or like sprawling university programs. So we're pretty much on our own and building this stuff. But we've made good progress and it's really awesome to have an internet community. So I want to thank the Reddit Robotics group for inviting us back this year and letting us talk about what we've been up to. So I got a presentation here. Let me just go ahead and start it. Let's see. Share screen. I think two. All right. All right, we can see it. Make sure this. Okay, there you go. All right, cool. So like I mentioned, our task at Human Mode is just working each year to make incremental improvements on the physical bots and also on our synthetic intelligence. Right. We build a lot of prototypes. It's very iterative. We just move on to the next after the last, and each one is meant to challenge us and teach us something new. We don't really put a lot of focus on aesthetics on these robots. Really, it's just about problem solving and forcing ourselves to improve. So in the past, we started our robotics program with these robots on the left. They were really interesting because they were all controlled through VR. So we called them the Gemini because they mimicked your movement whenever you controlled them through VR. And VR is actually a really big part of our company. In fact, the other team at Human Mode has been working on immersive VR metaverse called Massive Loop since about 2018. So this theme of like extending your presence into a physical or digital avatar runs really deep at our company. And we'll likely continue to improve it in our robots. But more recently, in the past 18 months, we tried to focus on two specific areas. One was improving our ability to do simulation so that we can iterate our design in software instead of just through hardware, trying to approach a one-to-one match between our physical and the simulated environment, and then also early work on legged robots. So to accomplish this, we built a few versions of a quadruped that we called the Lynx. There are three versions of the Lynx. One, it was electrically actuated. The second was hydraulically actuated. And then the third is the Lynx AI, which is a mini bot that we use for AI training. And this robot actually taught itself to walk in simulation, which is pretty cool. I'm going to go ahead and turn it over to our team, team lead, Jonathan Gilmore, Mehul Kumar in AI, Bao and mechanical, and Jay Choi in software, so they can describe these projects in more detail, starting with Bao and mechanical.
Thank you, William. So I'm the mechanical engineer. I oversee the design and prototyping process. I want to start off by giving an overview of our design process. So the cornerstone of this project focused on making a robust and lightweight quadruped system. The goal was to have the weight distribution focus on the upper body of the robots, creating a low inertial leg for the quadruped. Hence, the actuator being assembled at the shoulder for all three joint movement on the leg. We also use CAD and simulation program in our process as well. Regarding the CAD is used to find ideal arrangement for the component. Essential criteria like the material property, the moment of inertia, and the center of mass all play important role in the assembly of the quadruped. And then simulation was also done on the articulated model as well for this to prove that the movement is successful. When it comes to producing the part, we went with 3D printing and CNCing for custom component. And then we also used some 80-20 extrusion components for the ease of assemblability, which was essential when it comes to buying off-the-shelf components. When it comes to actuation selection, we wanted an actuator that have the ability to backdrive and have compliance for it as well. I want to pass it on to our software engineer now, Jonathan Gilmore.
Mic check. Okay, hi, I'm Jonathan. I do the electrical and low-level software. So the first, this is the first links we built. This is the electrically actuated links that uses the MIT Cheetah motors, and we built this primarily as a platform just to learn about what it takes to walk on 4 legs. We built it to just experiment with different algorithms and basic gait patterns. The next robot that we built was the hydraulic links, and that had pretty much the same goals as the first one. We built it to just experiment with, just as a platform to experiment with. We also wanted to try porting over everything that we learned from the first robot onto this second one, this totally different platform, and see how much of it carries over. And we also wanted to experiment with hydraulic systems. The third robot, now this is just a really small, lightweight robot, but we wanted it to be really easy to fix and repair. So it doesn't have anything special on it hardware-wise. It's mostly just, you know, your standard off-the-shelf hobbyist servos. But we wanted this one to be able to be repaired easily, because as opposed to the first two, which are running on these manually coded algorithms with, you know, inverse kinematics and all that, and these pre-programmed gait patterns, this third one is running entirely off of AI. There's no inverse kinematics, no hard-coded gait patterns or anything like that. It's just pure AI controlling the servo angles. So, you know, it's AI. It does some unexpected things sometimes, so we didn't want it to just, you know, freak out and break. And if it did, then we could fix it easily. So I'm gonna turn it over to Mehul, and he's gonna get into more in depth about that.
Hey, so I'm Mehul. I work with AI at Human Mode. So in the past, if you've seen our presentations, you know, we've used AI before, but it was mainly as a tool to like help with navigation and like, you know, do some object detection, collision avoidance. But now our goal was to build like a fully autonomous system, right, that can learn to walk on its own, like no user input, you know. It's able to, you know, solve hard problems, you know, do navigation, go over obstacles, and you know, and also be like modular, so that, you know, we can take the same, you know, system that we have built and use it in the future to train, like, you know, different robots. And it's not just for like, you know, locomotion. We can also train it to do like, you know, complex challenges in simulation. So the first step was to build or find like a game engine or simulation platform that can, you know, closely replicate real life and like be as close as possible, like 1:1, right? So one of the challenges in doing that was to like match the friction, right, between the floor and the feet of the robot. And there are a lot of like stuff involved in that, with like restitution and dynamic static friction. And some of the other challenges were like the center of mass of different, like, you know, parts. When you just like bring in a 3D model is different from like, you know, creating like an actual robot, and the center of mass of those parts might not be the same. And another problem was with like, you know, game engines and other simulation platforms. Things kind of seem like, you know, blown up. Like they're not like 1:1 scale. Like things are like kind of extra in those like simulation platforms. They are like built to like, you know, have huge explosions, like do massive flips. So they don't really match the real world 1:1. So our goal was to like explore different platforms and find like the best one that we can use to do some simulation, and to build like a virtual gym, right, with different obstacles, navigation, and different challenges, so that we can train our robots in there and see what they can do. So you see the links mini walking, that was the end result of our experiments. So we have we've trained a reinforcement learning model to like, you know, learn to walk from scratch and get over obstacles and navigate and turn based on like, what it needs to do. And yeah, this is this will really help us in the future as well when we have more complex robots that cannot, you can't really expect to write like 900 lines of code per action, right? So now I'm gonna revert back to William to talk about our advancements in VR control.
Yeah. Okay. So we've, we continue to work on improvements in VR control. The early version started with what we called the mech suit, which was sort of like a VR, I guess a mocap suit primarily, but also with the goal of really controlling physical avatars. One of the issues that we had back then was depth perception, because the vision was basically mapped to a flat plane. So we really couldn't utilize it for, grabbing things remotely. But we've continued to update that, and you can see in kind of this experiment, we have a pretty good ability to grab and manipulate items remotely while viewing them through VR. So Jay would normally be talking about that. He's not available right now, but we continue to advance that side of it in all these features. So we have, trained walking, VR control remotely, and then also just general walking and gait. They'll all make it their way into our next prototype, which we'll start working on here at the early August. So we're excited about that, and that's pretty much what we've been up to. So I don't know if there's any questions.
Yeah, well, thank you guys so much. I mean, you guys have come a really long way, even from the presentation you showed us last year. So this has been really fantastic to see your progress here. Yeah, I had a question. Never mind. We have some questions in the chat.
Okay.
Are there a lot of robotics enthusiasts in Oklahoma City?
Well, we're here. And we're enthusiastic. We're enthusiastic enough for everyone. So I think we'll help spark that. So that's our goal.
Good. Yeah, that's good. And then another question is, are you guys working with NVIDIA Isaac at all for your simulation environments?
Yeah, Mehul can talk more about that, but definitely, I mean, we use them all. I mean, we use Unity because we have a lot of familiarity with that. We use Isaac Sim. We use, I mean, but we basically spent the last 18 months like exhausting research in them. Mehul can talk more about it.
Yeah, I think Isaac Sim worked the best for us, but like William said, we have tried pretty much everything else that's out there. But I think Isaac Sim is pretty good. It has some issues in Windows, but in Linux it works pretty well.
Okay, great. And then I had a question, which is, have any of your robots seen any kind of real world applications in terms of like, are you contracting with any companies that are, using your robots for inspection or anything? Or
no, not yet. We're just still, working on kind of building a base of capability so that we can focus it on, specific, I guess end goal. I don't really like to approach that too soon because I think there's plenty to research, and anything we'd build would be less capable than after we've kind of forced ourselves to go through these exercises. So mostly it's just incremental design and building right now.
Absolutely. Okay, great. Well, thank you again for such a great presentation.
Thank you.
I really appreciate it. And great job coordinating between 5 presenters. That's the first time we've seen that. So thank you for that.
Thank you.